From the day we first started learning to program, humanity has had three ways of repeating the instructions we feed to a computer. The first, and simplest, was also the least useful. Copying and repeating code, while straightforward, doesn't scale, and wasn't particularly environmentally friendly on punch card computers. So, humanity invented the jump instruction, allowing early programmers to jump back to previous instructions and execute them again until a certain condition was met. Over time, this evolved until the invention of Fortran, which solidified the jump into the first type of structured loop, the do loop. Now, we can use loops for ranging through collections, executing code while a condition is met, or, no, we won't talk about that one. Loops are great. Generally, they make programming easier, but there are some cases where we have to think about problems a little differently. And this is where our third and final code repeating champion comes in, functions. But Isaac, functions are typically used to call parts of our program from other parts, not for repeating code over and over. Well, functions have a bit of a superpower.
Recursion.
It's about time I teach you how recursive functions and other fun function goodness can not only make some looping tasks simpler, but actually replace every loop in your code. It's time to catch up to the functional bros. At its most basic, a loop is just a block of code that gets repeated. Loops are usually denoted using some form of scope, and when your program's execution reaches the end of that scope, it returns to the start until a desired state is reached. The only real difference with recursion is that it's not the programming language or runtime that determines when you go back to the start of the block. It's you. Recursion is just a function that calls itself, either directly or through one or more layers of other functions. By calling the function again, you're effectively restarting the execution of the function. Remind you of something? Unless you're running indefinitely, whether on purpose or because you got your less than sign backwards, you probably want your loop to stop at some point. In a loopy language, you define a stopping condition when you define your loop. Look at your typical for or while loops. They all have a clear condition that has to be met for the loop to continue. This could be a variable being less than a certain value, the end of an array, or when a valid input is received from a user. Again, recursion is no different. Ultimately, when writing a recursive function, you have two choices. You can either call the recursive function again to keep recursing, or you can just not. It's quite simple, really. One of the first things that most recursive functions will do is define a base case. This is the condition that, if met, will cause the function to exit without the recursive call, effectively ending the loop, and all we had to do was not call the function. But Isaac, what about my other loop construct? I can't fathom programming without my break and continue keywords. It's okay. A lot of people start that way, myself included. You just need a proper education. Like I said a minute ago, when writing a recursive function, you have two choices. You can either call the recursive function again to keep recursing, or you can just not. Want to break out of the recursion? Congrats! That's just another base case. Skip the function call. Fancy continuing to the next iteration sooner? Call the function early. That's basically all the continue keyword does anyway. It executes the jump instruction before the end of your looping block. The only thing that's really any different between recursion and looping is state. Recursive functions don't usually modify non-local state. In fact, in a lot of places you'll see them being used, they can't. But we'll talk about that in a minute. Whereas loops almost always rely on being able to modify non-local state, like by changing the value of a counter variable. In a recursive function, you create your state as you recurse, passing new arguments into your recursive function on each iteration. That sounds a bit hand-wavy, so let's look at a quick example in Gleam. This repeat function takes in a value to repeat and a number n, and returns a list with n copies of the value. You'll notice we also take a third argument, our list. This, along with n, is our state. On each iteration, we add a new copy of the value to the start of a copy of our list, then call the repeat function again with the new list and n-1, marking that we've completed a single iteration. When we reach n equals 0, our base case, we just return the list as is without calling the repeat function again. The list we're passing around gets built up over the course of the recursion, and never do we have to modify some outside state. This immutability is exactly why a lot of functional programming languages, like Gleam, don't have loops as an option, let alone as an encouraged practice. The particularly functional averse among you will be screaming at me right now. But you're making copies of your list. You're going to use so much memory. The stack frames alone are going to kill your computer. And yes and no. Recursion done improperly can use a fair chunk of RAM. But most functional programming language runtimes and compilers use special tricks to get around that, like last call optimization. Immutable languages can also reuse memory, like nodes in a linked list, as they can guarantee it won't have changed. That's all out of the scope of this video though. I've got a full tutorial on recursion and gleam coming up soon, so get subscribed to see that when it drops. And while you're below the video, you might as well like, comment, and check out this video's sponsor. As a programmer who makes online content for attention, I'm constantly looking for ways to improve my crafts, both coding and creating, which is why I'm thrilled to be working with Skillshare, who are sponsoring this video. Skillshare is the world's largest online learning community for creatives. They've got thousands of classes where you can learn from experts in film, design, freelancing, software, productivity, or just about anything else. It's a great way to pick up something new to take your career, hobbies, or side projects to the next level. If you want something more structured, Skillshare has learning paths, which combine a number of classes into a guided learning experience, so you can go deep on a topic. I've been using Skillshare to brush up on my editing skills using DaVinci Resolve. Mustafa Nassar's class has been great at teaching me ways to speed up my workflow when I'm creating videos like this one. You know what programmers are like when it comes to optimizing things, after all. And as a thank you for watching my video, the first 500 people to join Skillshare using the link in the description will get a free month of learning. That's a pretty good deal, if you ask me. Armed with all this new recursion knowledge, you could probably go away and start rewriting most, if not all, of your loops as recursive functions. But you might run into a problem. How on earth do you handle errors? In languages with exceptions, this can be pretty easy. You just have a top-level function with a try-catch block that calls your recursive function for you, handling any exceptions you throw from within. In languages with errors as values, this becomes minorly more complicated, but in return, you get a whole lot more visibility and control. If you want to see which side I fall on in the errors versus exceptions debate, you can watch the video in the top right of your screen now. Gleam, inspired by the ML family of languages, has a result type, which is a union of either a value or an error. We have a couple of options if our recursive function returns an error type. The first, and most obvious, is to exit early by not calling the function again when you receive an error, passing the value back up to the caller as the stack unwinds. This is simple and often what you want, but it will always stop when it encounters the first error. There are often cases where you want to be able to run through all of the items in a list, collecting both the successes and the errors for later use. You can do this one of two ways: either build up a list of results and partition them later, or have your state be a tuple containing two lists, one for your value type and one for your error type. The latter can be more efficient, but it may be harder to see which error comes from which iteration. But anyway, guess what? If you've just used a result type, you're a real functional programmer now, because the result type is a monad. Scary, but true. After all of that though, I have a bit of a confession to make. Even in functional languages, it's rare that you'll ever have to write a recursive function yourself. That's right, you've been tricked into thinking the only way to replace loops is all this difficult boilerplate. But in fact, we're saved by a little thing called higher order functions. What are higher order functions? They're just functions that accept other functions as input, and most functional languages will have standard libraries full of recursive function implementations for you to just pull off the shelf and use. Want to transform every item in a list? You'll need list.map. Need to compress a list into a single value? List.fold is here to serve. Just provide a function, often an anonymous one, to one of these pre-made recursive functions and it'll do all the hard work for you. I'll leave a link to the Gleam standard library's list module in the description. It's a really good example of what you're likely to find baked into your language. Of course, you can recurse over more than just lists. So let's discuss where recursion is better than loops. One of the obvious candidates is when you're looking to do any sort of graph or tree traversal. Each function can just look at a single node, keeping the code easy to read and understand. Your recursive function only needs to decide if it wants to check the next node in the tree, or just return, unwinding back up the structure to your root node. Recursion is also great when you're breaking down large problems into small ones. You'll probably run across it if you're studying the concept of dynamic programming, a common requirement in coding interviews. This typically uses recursion to break a problem down into small chunks, and then memoization to reduce work. Doing recursion properly naturally forces you to break down problems anyway, so it's a great fit. One neat trick that recursion has is that you can execute code after the recursive call. This can be helpful if, for example, you want to apply an operation to tree nodes starting from the leaves and going to the root, rather than from the root to the leaves. Deleting nodes in a tree is quite a good example of this. If you delete a parent before you delete its children, it can be quite easy to end up with orphans. This is called post-order traversal for you nerds out there. But despite everything I've said so far, loops do have their place. They're conceptually easier for beginners to understand, and they can also be more performant than recursion if you're not using tail call optimized recursion, especially if you're iterating over a contiguous chunk of memory. Your CPU can do lots of optimizations to help speed things up there. That said, for 99% of applications, the difference in speed at which your programming language recurses versus loops is going to be negligible. If you're going to complain in the comments that recursion would make your zero-user CRUD app slow, I want to see proof that every other part of your code is totally optimized, especially any I/O your app is doing. Your database queries will be orders of magnitude slower than a bit of recursion in nearly all cases. Basically, if you want to moan, bring receipts. But you're now a recursion expert. Go forth and recurse and get rid of those pesky loops. And let me know in the comments which problems you're going to consider tackling with recursion. Don't forget to check out Skillshare using the link in the description. Remember that the first 500 people to join will get a free month. A massive thank you to Skillshare for making this video possible. But anyway, it's time for you to take a step back from YouTube, tell your family that OOP and looping are dead, and join the functional resistance. See ya!